Hi, so I'm Liam, and this is the WireFrame Rotator. It's a pretty obvious name, but what it does is it rotates wireframes. So a wireframe is, as you can imagine, just any 3D shape that's kind of shown with just lines between vertices.
Alright, so here's a quick demonstration of how to actually set up the device. So when you first turn it on, you're going to be greeted with this screen, which says, "Welcome to the wireframe rotator." To get rid of that, you just press the select button, and then it's going to ask you to input the number of vertices that you want. For the demonstration's sake, I'm just going to say I only want 2 vertices, and then I again press the select button to confirm that. So now I can enter my points, or coordinates, in 3D space. And I'm just going to go with a straight line between the coordinates 1, 1, 1. And then I can flip the switch that determines the sign of the value. And then I can input -1, -1, -1. So now I can input the number of edges that I want. And, well, I can only have one edge between 2 points, so I'll go with one edge. I'll press the select button. And now I input the edge table, which is essentially an array that treats each point as an index in the array. So I had 2 points, and those are going to have indices 0 and indices 1. So now we have that line rotating, which is the line between 1, 1, 1 and -1, -1, -1. So now if I want to change what's rotating, I can go ahead and I can press either one of the preset buttons. So for example, here's a cube. And then the other preset button at the moment is a very poorly drawn Aces logo. Sorry, it's a bit glitchy. It's also upside down. It's pretty poorly executed, this one.
So firstly, before going into how this works, I want to talk a bit about the design that went into it. So here in front of me, I have the PCB, that is the wireframe rotator. And as you can see, there's pretty much 2 ports for each of the main components, which is the LCD screen and the keypad. So basically this is because this is more of a breakout board, and as you can see there's no microcontroller up top, but that's because the microcontroller is actually within the case. So the actual LCD attaches here, and the keypad attaches down here, and then the lines that control them attach here and here, and they are directly linked to the other lines. And then here there's a button that can control whether or not what you're inputting is a positive or negative number. And here's what was supposed to be the select button, but it's miswired, and then just some debounce stuff over there. The other PCB that was used in this project is this nice little 3.3 and 5 volt regulator PCB. The internals are messy to say the least, but you can clearly see the 18 mega half-size Prima proto board that's in there controlling everything, as well as the 3.3 and 5 volt regulator. And then each corner has a heat set inset for some screws to screw on the top PCB. So coming back to the case, you can see that there's 2 buttons on the front side, and those are 2 preset buttons. So essentially what that means is that after the setup of your shape, you can press either of these to load a preset shape. And currently the cube is actually one of the preset buttons. It's this one right here. And then if I turn this case around, you can see over here there's a button. And this was supposed to be the reset button, but since the select button isn't working, it's now functioning as the select button. Over here on the other end of the case, we have the barrel jack for the power input. So now let's talk a bit more about how you can make your own wireframe rotator. So this is pretty much the theory section. So we can make a checklist out of things that we need to be able to do this, and that checklist has 3 things on it, and those are: we need to be able to rotate points in 3D space, we need to be able to map 3D points onto a 2D screen, and then we need to be able to draw lines between 2D points. Luckily, the third one is already done for us, because with the LCD, it's pretty much necessary to use a library, and all libraries that control the LCD already come with line functions. So starting with rotation, the first important thing to understand is that while we're rotating 3D points, the rotation itself is actually 2-dimensional. And you can see that with this animation on screen because all the points rotate through the path of a 2-dimensional circle. And this is because even though the rotation affects 3-dimensional points, there's one value that always stays the same, and here it's the height value.
So really we only need to be able to rotate points in 2 dimensions. And luckily for us, there's something called a rotation matrix that can help us with that. So this here is the 2-dimensional rotation matrix, and while it looks a bit scary, it can be broken down to this easier equation on screen. So this Desmos graph that I made shows how rotation matrices work. So essentially here we have these 2 equations that solve for both x and y, and don't worry that they're called a and b, you just can't use the variables x and y in Desmos in the way I would need to. And I represents theta. So essentially as we move theta around our unit circle, we see that this angle is swept out over here, but this point always stays on this circle, so it's rotating around. So we're not only changing theta, but we're actually making it so this coordinate stays on this circle the whole time. And this graph also shows some other stuff, like theta on a bar line and the x and y in their own sinusoid waves, but that's not really important. What's important here is that we have some way that as we change theta, we can move a point around a circle, which basically means that we can just rotate a point by angle theta. Now for projection mapping. On screen now, I've made a little animation to explain projection mapping. So basically for projection mapping, you imagine that you have a 2D plane that represents your screen somewhere in a 3-dimensional world. And in that world you can choose a place for your camera, and then you have your object that you're trying to map onto the screen. And if you draw a line between your camera and the point that you're trying to map, and you find the intersection of that line with the screen, the xy coordinates of that intersection are the same xy coordinates that you are going to turn on for the pixels on your screen for the mapped object. What we need now is a formula that takes us from this representation to actual numbers. So if you imagine this scenario from a bird's eye view, you get something like this. You get a triangle between our camera and our point that we're mapping, and then some point that makes it a right angle. And then you also get a triangle between our camera and the intersection between the screen and the line. So out of these 2 triangles, we know the x-coordinate is the height of the big triangle, and the base of the big triangle is the focal length, which we know, plus the z-coordinate. For the small triangle, we know that the base is equal to the focal length, but we don't know the height. The height is what we're trying to solve for. That is the number we're looking for. But since we know the other 3 sides, we can build an equation to solve for the height. So if we now imagine this same scenario from a cross-sectional view, we can then also solve for the y, and then basically with that we can solve for any point that we're trying to map from 3D to 2D. And then our checklist is complete. So that's it. Thanks for listening.